I'm going to record this so that I can put it back up. So if you want to watch it again, you can. Okay. And specific heat capacity is dependent on what the substance is and how well it conducts the heat. All right. If you have a high specific heat capacity, you're well insulated and it doesn't conduct the heat easily. If you have, or it retains the heat. If you have a low heat capacity, then that means it can conduct the heat very well. And so it's going to heat up quickly or lose heat quickly. Okay. We talked about, see, I pre-wrote the topic so I wouldn't forget anything. We talked about the concept of enthalpy. Enthalpy is energy from breaking bonds. And we just call it heat. It's this, we can use them interchangeably. They are different, but for our purposes, we can use them interchangeably. And that is what we use for change in entropy. We can't measure enthalpy. We can only measure change in enthalpy. So delta means change, H means enthalpy. So we talked about breaking bonds and reforming bonds. So if you want to figure out the energy involved in making water molecules from hydrogen, you can look up bond energies, and you have those in your notes. Where it says bond energy 6.2. I guess I didn't assign it. Did I assign something? Okay, never mind. That's the assignment. Let's go back. Here, bond energy notes, back in March 1 through 5. Okay, so you have access to that. And then you have a thermochemistry packet that I gave, and then I think I gave you an updated thermochemistry packet. Heat worksheet. Heat worksheet set that has some of the information you need in it too. Okay, so just so you know where you can find that. And energy, enthalpy from bonds breaking and reforming, you do the bonds breaking and you calculate, add up all the energy, and then you subtract the bonds that are forming. Okay, so that's how you do bond energies. The next thing we looked at was figuring out the energy of a reaction using enthalpy of formation. All right. This up here is a formation reaction to make water. It's making 2 moles of water, but it's a formation reaction. It's making water from its elements. And again, if we look at classroom and we look at this heat worksheet set, these are heats of formation. So this is the energy it takes to make 1 mole of each of these compounds. And it doesn't take any energy to make aluminum because aluminum is an element. You can't make it. Okay. So enthalpy of formation, you do the sum of the products minus the sum of the reactants. So if you were doing the energy for combustion, say, of methane, two, three, four. So what you would do is you would figure out the energy for the products, which are right here. So whatever the energy is to make 1 mole of carbon, and then the energy to make 2 moles of water, and that you would sum that up, and then you would subtract from that the reactants, so it would be CH4, and then 2 oxygen, which would be 0 because oxygen's an element. Okay? Hopefully that makes some sense. And we did several worksheets on that. The next thing we looked at was Hess's law. Hess's law says that if you have an equation that you can't look up in enthalpies of formation for whatever reason, you can also basically add together different energies, different equations, enthalpies. So these are enthalpy of formation. You're going to use enthalpy of reaction, delta H reaction, because not all chemical reactions occur in one step. A lot of chemical reactions have several steps, but if you combine all the steps, they're going to add up to the whole thing. So that one, what we did for that, here's a Hess's law worksheet. Let me just, I don't know how well this is. That's probably not going to copy well. Let's do the easy one, the first one. So basically, if you want to figure out this, you could go and look up enthalpies of formation, but it doesn't happen in one step. It happens in several steps. So it may be difficult to find some of that information. So what you do is you want to recreate this by adding these together. All right. So we go through and we find Fe2O3, Fe2O3, is here. So this is the equation we're going to use because there is Fe2O3 on the product side, but we're not going to use that one. So we cross it out. It tells us we have 3. So we're going to multiply that guy by 3. And the rest of this gets multiplied by 3. 3 times 3 is 9. 3 times 2 is 6. 3 times 3 is 9. Now I'm going to pick a product. I'm going to try to find Fe3O4. Here's Fe3O4 here, but it's on the reactant side. Here it is on the product side, so I'm going to throw this equation out. I need 2 of them, so I got to multiply everything by 2. So 3 times 2 is 6, 4 times 2 is 8, 4 times 2 is 8, 2 times 1 is 2. All right. Now I've got Fe2O3 and I've got Fe3O4. I need 1 carbon monoxide. Notice I have 9 on the left and I have 8 on the right. What's 9 minus 8? 1. So now we have our 1 carbon monoxide. And I need 1 carbon dioxide. On the product side, I have 9 here, I have 8 here. They cancel each other out and I end up with 1. And then the only thing not accounted for is the 6 irons, but they don't need to be in that equation because they cancel each other out. And then you just add these guys up. Okay? And the ones you have are not difficult, I promise. All right. So that kind of sums up thermodynamics and heat energy. All right. Thermochemistry. That's actually what I should have written up here instead of thermodynamics, is thermochemistry. All right. Light energy, the energy from light. We talked about the electromagnetic spectrum. And we learned a song to help us remember that the electromagnetic spectrum is made up of all sorts of different kinds of light. We've got gamma rays, X-rays, ultraviolet 2, visible, infrared, microwave the food, turn on the radio and dance a little too. Okay, so if these are gamma rays, they are very, very small wavelengths. And as we go this way, our wavelengths get bigger. So these are high energy, high frequency, which means they wave a lot, but low, not low, small wavelengths. And for wavelength, we use that symbol. For frequency, we use the symbol nu. This is the symbol lambda. And energy is E. On the other end of the spectrum, radio waves are low energy, low frequency, and long wavelength. And those all relate together in that if you know the speed of light is equal to the frequency of a wavelength or the frequency of light times its wavelength. So you can solve for frequency by taking the speed of light divided by wavelength. You can solve for wavelength by taking the speed of light divided by frequency. Wavelength is, of course, or speed of light is, of course, 3 times 10 to the 8th meters per second. Okay? So we've got that relationship. What is it that causes that? Well, the electrons are living in orbitals. And Bohr took and studied the hydrogen atom. And, well, actually, before we get to Bohr, let's talk about Planck first. Planck is the first guy. They were looking at the light. They were looking at these transitions, and Planck said that energy is quantized, meaning it's in discrete energy packets. And Bohr went one further than that. He said, okay, that energy that Planck was talking about is what it takes to jump from one orbital to another. And if you don't have the right energy, you can't make the jump. So if your electron makes a large jump, it's going to take a lot of energy, right? And then it's going to release a lot of energy when it falls back. Oh, that's not going to work. So the bigger the jump, the higher the energy. A small jump, let's say you have electron here in this energy level and it goes that far, that small jump is going to be not going to relieve as much energy. So it's going to be, this would be less energy because it's a smaller jump. Okay. And that is what gives off light. That energy that is emitted is light. That energy is emitted as photons. The photons act both as a wave and a particle, which helps us define what the electrons are doing and where they are. Okay? Let me make sure I didn't miss anything. Oh, let's talk about the light that it gives off. Hydrogen gives off a spectra. If you look through a spectroscope, hydrogen gives off a spectra. I need a blue-green. And you can see the little lines. Those little lines are the discrete packets of energy. All right, so if you were looking through a spectroscope at a tube of hydrogen, the electrons are going to be jumping back and forth and giving off that energy in those four amounts. That's all we can see. It gives off other energy in the infrared area and in the ultraviolet radio, but we can't see that. All right, so that's what we call an emission spectrum. And those are fingerprints. And I can't remember who it was that discovered helium, but when helium was discovered, we didn't know about any of the noble gases. When Mendeleev put his periodic table together, we didn't know about the noble gases. But helium was discovered because they were looking at the sun and they were looking at the spectra, and they came up with a different set of lines than hydrogen. And they're like, that's a new element. And they named it helium after Helios, which is Greek for the sun. All right, so on to where the electrons live. So the electrons live in orbitals, and there are four types of orbitals. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And they are in the different energy levels. So we always start counting from the bottom energy level. The first energy level, n equals 1, has s orbitals. The second energy level, n equals 2, has one s orbital and 3 p orbitals. The third energy level has one s orbital, 3 p orbitals, and it has 3 d orbitals, but I'm going to put those in a different color because in a minute or 5 d orbitals, we're going to talk about that. N equals 4, you have an s orbital, you have 3 p orbitals, you have d orbitals, and you also would find f orbitals. Okay, the electrons live there. Depending on how much energy they have, that is going to determine which orbital they're in. Okay, and when we fill electron orbitals, you can use this graphic. The Aufbau Hotel chart, and it's on a Jamboard so that you can write on it. You can use this graphic to fill the orbitals, and you have to follow these rules. The orbitals you have to start at the lowest price room closest to the nucleus, and you fill in the order that's listed here. And the reason 3D comes after 4S is it's a little more expensive than 4S. After it's filled up, these settle back into the third energy level. So they belong to the third energy level. They just don't fill in quite the right order. And you have access to this in your stuff, so you can pull this out to use when you take the test to do electron configurations. Okay, so electron configurations, you just simply put your electrons into that data table. So if you're doing an electron configuration for sodium, sodium has 11 protons and 11 electrons. So if we put them in, I guess I can do it on this Jamboard. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the code for that is 1s2, 2s2, 2p6, 3s1. Okay, you can't have more than 2 electrons in a box. The 2 that are in there must sleep separately, opposite. And Hund's rule says you don't double book until you have to. Okay, so 1s2, 2s2, 2p6, 3s1. If we're talking about quantum numbers tell you which specific orbit you're talking about. So the n number equals energy level. The L equals orbital shape. The ML tells us the orientation, or the room number. And they go, if you have your L number, they go from the negative L to the positive L. So if your L number is 0, you have only 0 for your room numbers. If L is equal to 1, you have -1, 0, +1. If L equals 2, it starts at -2, -1, 0, +1, +2. L equals 3, -3, -2, -1, 0, 1, 2, 3. And then the last quantum number is ms, which is your spin. And if you're spinning up or clockwise, it's +1/2. If it's spinning down or the other direction, it's -1/2. All right, so those are your quantum numbers. Let's see if I've missed anything. All right. Oh, I left out, got to type in here. Periodic trends, we're simply talking about the periodic table. So when you're talking about periodic trends, you're talking about the electron, the valence electrons, in a family, and how the number of electrons versus protons affects each other. So if you think about the second energy level, N equals 2, we have lithium, beryllium, boron, nitrogen, carbon, nitrogen, oxygen, fluorine, helium. As you go left to right, the radius of those decreases. I'm not doing a very good job of that worked. The radius decreases, and it decreases because the protons increase, and they pull those in tighter. When you then go to the next energy low or next row, you're going to get a much larger, you're going to pop back up and get a larger radius, and then it's going to start to get smaller again. One, two, three, four, five, six. So aluminum, silicon, phosphorus, sulfur, chlorine, and then it's not helium, that's neon, and this is argon. Okay, so what does that what causes that? What are the trends we see here? Well, as you go down for atomic radius, the radius decreases across and increases going down. So let's get a different color. So this is the radius trend. There we go. Now, if you have an electron out here, it's going to be easier to pull off the further it is from the radius. So the ionization energy, the bigger the substance is, the bigger the ionization is going to, energy is, I'm sorry, the smaller the energy is going to be. It's going to be easier. So ionization energy is the ability to remove electron. So the farther you are from the nucleus, it's easier, so it's less energy. So as you go down the periodic table, the ionization energy decreases. It increases going up, and then it increases going across. Okay, so it's kind of the opposite. The same goes for electronegativity. Electronegativity is just how attractive the electron is. And again, small radius, more attractive. Okay? All right. Now we're on to Lewis structures. Lewis structures are talking about covalent bonding. Which is when two electrons share. The orbitals overlap and the electrons share. This kind of bond is a sigma bond. All covalent bonds have sigma bonds. Okay. What you have to do for Lewis structures is you have to count your valence electrons, and then you create the Lewis structure with the dots. So, if we want to do a Lewis structure for water, hydrogen has 1 valence electron, and there are 2 of them. Oxygen has 6 valence electrons. How do we know? We use the happy atom chart. So there's a total of 8 electrons. We draw our skeleton. Then we add our extra electrons in. So we have 2 electrons here, 2 electrons here. So we have to add 1, 2, 3, 4. So that totals 8. Okay. If you have extra electrons, they go on the middle. If you don't have enough, you double bond. You don't have enough electrons, you double bond. There is, you guys did, here's your happy atom chart. Here's instructions on how to do a Lewis dot structure. That was just another video I found. Here's Lewis structure worksheets. There's a PDF. I also made a Jamboard of it, so you can go on the Jamboard and draw the Lewis structures. And Crash Chemistry Academy does a nice job of explaining Lewis structures. Okay? So, Lewis structures are simply drawing out the molecules. Now, the molecule or the bonds orient themselves using the VSEPR model, which is valence, electron, shell, repulsion theory, or VSEPR. What am I doing wrong? There's a P in there somewhere. Electron pair. So it must be valence electron shell. Valence, I know what it is. Valence shell electron pair. So it's VSEPR, VSEPR. And what that says is the electrons want to be as far apart from each other as they can. Okay? So when you draw a molecule, if you're drawing, an atom, if you're drawing, or a molecule, water, let's do water because we just did it. Water has 2 bonds, but it also has lone pairs. They take up space. So right now it looks like they're 90 degrees apart, but you can actually shift in 3D and be 109 degrees apart. And what happens here is, remember that oxygen has, in his second energy level, he has a 2s orbital, and then he has, oh, I drew too many of those, 2p orbitals with 4 electrons, and these guys merge and they become a hybrid orbital, and we take those 6 electrons, 1, 2, 3, 4, 5, 6. These are your lone pairs, and these electrons are bonded to the hydrogens. Okay, so we hybridize. If we have two bond areas, which mean domains, let's call them domains because that's what we called them in class. You have an s and one p orbital involved. That means there's two more p orbitals out there not in use. Three domains, you have sp2. So two domains is just going to be like that. Three domains is going to be like this. If you have four domains, four bonds or a combination of bonds and lone pairs, that's sp3. And for that one, we have to draw a little bit different because it's three-dimensional. Five domains, because some atoms can have more than 8. sp3, and we pull in a d orbital. So now we have 5 bond areas and then 6 domains, sp3d2, and 1, 2, 3, 4 at 90 degrees. And then there's another guy coming out and one guy going back. You have in your things where's the one we did? This. No, that's not the one you guys have. You have this one that goes along with that web page. So we wrote the names of all the geometries down. We wrote their names down. If you don't have them, I added into Classroom, and it's not hooked anywhere, a basic chart that you can use. All right, so this has your domains. It says electron dense areas. I don't know why we can't all call them the same thing. But this guy's no lone pairs. There's the names, 1 lone pair, 2 lone pairs, 3 lone pairs. So there's that information for you. Okay. All right. So we talked about the hybrid orbitals. We talked about the bonding. The only other thing that we did talk about this. I just haven't done it in the review yet. We talked about that here's the oxygen, the water molecule. So he's got a bond that overlaps with hydrogen. He's got that bond that overlaps with this hydrogen, and then he's got the lone pairs, right? Okay, so what if we have 3 domains? What if we do BF3? Boron is an exception to the rule. It can deal with only 6 electrons in the middle. So BF3 would look like this. So does he need sp3? Does he need all 3 p orbitals? No. So one of these orbitals is the s orbital that's changed, that's bonding with the f. One is a p orbital and one is a p orbital. So you've got those guys overlapping. So I'm going to label these. This used to be s, this used to be a p, this used to be a p. So we're at sp2. But there's still a p orbital on that boron. And the fluorine's going to have p orbitals. Well, that's not a good example. Let's do nitrate. If we draw all our electrons in, nitrogen has 5, he has a -1 charge. So that's another electron. 6 plus 18 is 24. So here's 2 electrons, 4 electrons, 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This nitrogen doesn't have 8 around him. So we have to double bond one of these. So we have 2 bonds there. That's 1 bond. That's 1 bond. Okay. So that nitrogen bonds, here's the S, here's a P, but there's still an unused P. I wanted that in a different color. There's the unused P. And the oxygen, he's got, these lone pairs are in an s orbital. These lone pairs are in one of the p orbitals. And then there's a sigma bond in a p orbital. So he also has an unused p orbital. And those can overlap. And that's what we call a pi bond. A pi bond is another bond out there above or below the sigma bond. And one of the questions on your chart asks you to identify geometries in molecules. Let's find a big molecule, shall we? Let's do, let me think. Yeah, let's do math, crystal meth. I only know this because last year we did a thing with drugs. Okay, so here's what he looks like. I'm going to take a picture of that. All right, at each of these points where the line bends, we have a carbon. Each of these carbons, this is what we call a benzene ring, have a hydrogen coming off of it. So each carbon now has 4 bonds. So this geometry, there's a double bond there. That double bond, we have a sigma bond and we have a pi bond. So this geometry, we've got 1, 2, 3 areas. So this is sp2. This carbon, we have 1, 2, 3 areas. This is sp2. sp2, sp2, sp2. This carbon has 2 bonds, which means he's going to be bonded to 2 hydrogens because he has to have 4. This is a shorthand way of writing it. I wouldn't expect you to be able to recognize this because this is organic chemistry. But if he has 2 hydrogens he's bonded to and 2 bonds, this is sp3. This guy here is also going to be sp3. This carbon is bonded to 3 hydrogens, so he's also sp3. Nitrogen has a lone pair on it, so that guy is also sp3. So that's how you figure out, and I've given you, when I draw it out, I draw all the pieces out, so you don't have to worry about trying to figure out how many hydrogens the carbon has. So that's how you figure out what the shape of a bond is in a particular molecule. Okay? Now, sigma bonds. Let's count our sigma bonds. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 sigma bonds, which means single bonds. But we also count the pi bonds because they have both a sigma and a pi. A double bond means you have pi and sigma. How many double bonds do we have on here? We have 1, 2, 3 double bonds. So we have 23 sigma bonds and 3 pi bonds. All right. If I give you this molecule, let's count sigma bonds. Here's 1, 2, 3, 4, 5, 6, 7, 8. And then only 1 pi. One pi bond. Okay? All right. Questions? So that sums it up. There aren't any questions about polarity on the test. Oh, I lied. There is one question about polarity on the test. I think I'm going to take it off. No, we need to do it. All right, so let me do one last set of conversation here. We need to talk about intermolecular forces. All right. Okay. Last topic. If a molecule shares equally they are nonpolar. If a molecule shares electrons unequally or isn't symmetrical, meaning it doesn't pull evenly in all directions, it's what we call polar. Okay? To figure out if a bond is polar or not, you look at the electronegativity chart. The bond, we look at the electronegativity chart. So on your classroom, happy atom chart has an electronegativity chart on it. So if the bond electronegativity difference is 2.1 or higher, it's considered an ionic bond. If the electronegativity difference is between 0.5 and 2.1, it's considered polar covalent, and less than 0.5 is considered nonpolar. So you look at the electronegativities. Okay. If the electronegativity difference is greater, is that the greater than sign or less than sign? I'm not sure. No, this
Less
is
than.
yeah, that's greater. It's 2.1. It's ionic. If it's 1.5 to 2.1, it's polar. And if it's not 1.5, is 0.5. And less than 0.5 is nonpolar. Okay. Now, if it's a polar bond, it exerts an intermolecular force. There are 3 intermolecular forces. We just talked about this last week. The hydrogen bonding is the strongest. It's when you have hydrogen connected to nitrogen, oxygen, or fluorine. If we look back at the molecule we drew right here, there's a hydrogen bond. Okay, this molecule is going to be polar because it's not symmetrical, and the hydrogen bond is going to make it even more polar. So this has, it exhibits hydrogen bonding. Okay, the next kind is dipole, dipole. Dipoles are polar molecules without hydrogen bonding. And then London dispersion forces are in all molecules, but they are the only ones in non-polar. And they're temporary dipoles or instantaneous. Okay, now, intermolecular forces cause liquids and solids to form. And we can take a phase diagram, and this is pressure because the two things that affect gases are pressure and temperature. They will affect everything else. So when you look at a gas diagram, here's 1 atmosphere. At 1 atmosphere, what temperature does water melt? What's the melting point of water? What's the freezing point of water? And what temperature does ice freeze? 0 degrees Celsius. So we would have a line somewhat like this. And on this side, we have a solid. And in here, we have liquid water. I didn't draw that very well. Let me copy and paste. It'll just be easier on everybody. I don't know where my here, we'll do it this way. Phase change and diagrams. I don't know why I can't find the phase change. Remember we did this together. So here's a phase change diagram for, is this water? No, this is carbon dioxide. Yeah, this is water. Okay, let me copy and paste it. So, at 1 atmosphere, what temperature does water melt at? It melts at 0 degrees Celsius. At 1 atmosphere, what temperature does water boil at? It boils at 100 degrees Celsius. So that's how you read this chart. If you can get water down to a fraction of an atmosphere, 4.58, remember 760 is 1, so this is a fraction, you can reach a triple point where you get solid, liquid, and gas all existing at once. Otherwise, if you go from this side of the line to this side, you're melting something. So if you're at 2 atmospheres and you want to melt water, you're still going to be at about 0 degrees. But if you're at 2 atmospheres and you want to boil water, you're going to have to crank that temperature up way above 100 degrees Celsius. Okay, if you're less than, let's say you're at a half an atmosphere, you're still melting at around 0 degrees Celsius, but now you're going to boil less than 100 degrees. Okay, and that is a phase change diagram. So on a test, you probably would be asked something like, what goes here? What goes here and what goes here? Well, what do we put in here? We put solid. What do we put in here? Liquid. And we put gas in here. Okay? All right. Now, I think we have covered absolutely everything. All right. I had a question about what this review was. The review is for the test on Thursday. We've talked before, but let's see. Is Synergy open? No. Believe it or not, even though I've used Classroom the entire year, I have kept the learning management system up to date here. So let's look here. Why am I missing dates? Well, that's nice. Somehow stuff didn't copy. So this is the week of May 10th. Mother's Day was May 9th. So this is not next week, but this is the week after. May 11th is our final. Everybody, juniors and seniors, take the final. And you guys are going to get a review probably as soon as on Thursday. Okay? I just need to figure out what I'm going to do for the review. So this is, I don't have next week. Let's see if it's saved to 4th hour. Yeah. This is this week. We have the test on Thursday. And then next week, yeah, it didn't save there either. Okay, we're doing it this way. That's calculator. We're not doing it that way. Let's look at this calendar. Okay, here's where we are right now. I can draw on this and I'm not sharing. So it doesn't matter because you can't see any of this anyway because I'm not sharing. What is wrong with me? Here's today. Hello. Okay, this is today. Thursday, we're taking the test. Next week, we have class on Monday, Wednesday, Friday. Those are all going to be review days. Again, I am going to go through and review each day, and we'll probably ended up with about 25 minutes to work on the review, but hopefully what I've done has helped. I'm going to go through and review each quarter. Okay? And then we take our final here. On the 13th, we'll only have juniors, and on the 17th, we'll only have juniors. And you guys will need to check in with me, and then we'll talk about what we're going to do from there. And the day for finals for 2nd hour for the rest of the school is here. So once again, juniors, you'll have to check in that morning. But we won't have a final because we've already had it. So you just have to check in and then go away. All right. Does that answer that question? Now I'm ticked off about that. Okay. Now I got another question. The JUCO kids are taking the final online. It's not like the math final where you have to take it at JUCO. I get to administer it. Now, because it's the JUCO final, there's a couple things I have to follow, and that means you guys are going to have your screens on. Okay? I've got to be able to see you. I am going to let you guys use OpenNote on the final because I can't control that anyway. So But that's the deal for the final. Questions? Anybody stuck on any of the questions in classroom that they want to ask? Not classroom, mastering chemistry.
Actually, yeah.
Okay.
It's on part 1, and it's question 10. But
You want
there's
to share your screen?
Yeah, I can do that.
Okay.
Can you see?
Okay. So, thinking about the JUCO final is the same one we're taking in class. Everybody's taking the same thing. All right. So did I not put this on this tab? Oh yeah, here we go. Okay, so the 2s orbital, is it going to be here, scroll over so I can see the right. Okay. The 2s orbital should be larger than the 1s, right? Let's look at our choices. The 2s orbital is the same shape as a 1s orbital, but it's going to be larger. All right. The 3p orbital would have the same shape as the 2p orbitals, but it's going to be larger. Same shape but larger. And the 2s and 3p orbitals have more nodes, which means more waves.
Oh, okay.
That's a good question. Thank you for asking it.
Mm-hmm.
The next question was, what percentage of our grade will the final be? If you are taking it for JUCO credit, the final is worth 20%. If you are taking it for regular credit, it's going to be a third of 40%. So whatever 1/3 of 40 is. 15%, 12%, 12 times 3 is 36, 13%, about 13%. Am I going to make a copy of what I just went over today? I'm actually recording this. And so, yeah, I will post that. And I'm going to print out the note page that we just did. And I'll scan it into a PDF and post it. Anyone else with questions? If you have questions tomorrow and you want to Zoom, I have 5th hour plan, which is when you guys are eating lunch. So I would be happy to have an open Zoom tomorrow at 11 o'clock from 11 to 11:45, because I can eat lunch after that, because I have 5th hour off. So that would be easier. I mean, if you want to try to Zoom in today during advisory, I've got some kids coming in. It gets kind of hectic, but I could give you guys undivided attention if you wanted to Zoom with me during that 45 minutes to ask questions. And I can send out a link for that. If you have other questions, send me an email and we can set up a time. I can Zoom after school a little bit on Wednesday, but I could Zoom longer in the evening if I needed to. I mean, I'm willing to be flexible. We will have a little bit of time to take questions on the test before we start on Thursday, but you're going to want the whole time, I think, to work on it. So we won't do more than a couple questions. Why is this pink? Why do I look pink? Now I feel like I've got purple. I turned a light on. I still feel like I look pink. Oh well. did that not work? Oh, 19th and 26th. All right, guys, have a great day.